people.
Yeah, people coming in.
Yeah.
Right. See that number jumping up. Maybe I'll just kick off in any case. Hello and welcome everyone. My name is Zheng He and I'm the research project manager at the Center for Eye Research Australia. I'd like to thank you for joining us today for the discussion utilizing deep learning to analyze Stargardt disease progression. Today's webinar is part of the series focusing on application of artificial intelligence on healthcare. Thanks for the generous support from the Medical Research Future Fund. We hope with this series, we can help connect the clinicians and AI scientists to work collaboratively to develop AI solutions for real-world clinical problems. In the next hour, we will hear a presentation for about 45 minutes, and then we will have some time for Q&A and discussion. So please feel free to send in your questions and your comments in the Q&A box as we go, and we'll get through as many questions as we can after the presentation. Just a note that this session will be recorded and will be made available for open access on our YouTube channel later. And this event is jointly hosted by Center for Eye Research Australia and Monash University E-Research Center. Before we welcome our speaker today, I'd like to introduce my co-host, Dr. Zhongyuan Ge, who is an associate professor and a deep learning expert in Melbourne, in Monash University. Excuse me. So, Zhongyuan, maybe I'll hand over to you to introduce and welcome our speaker.
All right. Thanks for your kind introduction, Zheng He. So we are very honored to have Dr. Jason Charng, who is a research fellow from Lions Eye Institute, and also a senior lecturer from Department of Optometry from the University of Western Australia. So I just briefly read out his bio. So Dr. Jason Charng completed his PhD at the University of Melbourne, followed by a postdoctoral fellowship at USA, UPenn. So he currently works at both Lions Eye Institute and the University of Western Australia, where his main research interests are utilizing artificial intelligence, AI, machine learning to analyze ocular images, as well as exploring structural and functional assessment for trial endpoints in inherited retinal degeneration. So thanks very much for joining us, Jason. So I will hand over to you to let you start your talk.
Thanks for the kind words, Zhongwan, and thanks, Sarah, for this opportunity to present our work here at Lions Eye Institute. And just a full disclosure before starting the presentation, I confess I'm not a computer scientist. I'm a clinician scientist with research interest in structural and functional assessment of the retina, in particular, gearing towards outcome measure for retinal gene therapy. And this is a project we did with computer scientists at CSIRO in utilizing deep learning to analyze images taken from eyes with Stargardt disease. So let's just start with introduction to what is Stargardt disease. So Stargardt disease is a genetic mutation that arises from mutation in the ABCA4 gene. The ABCA4 protein is produced in the photoreceptors and has been shown to localize in the photoreceptor outer segments. The critical function performed by ABCA4 protein is to remove waste product from the phototransduction cascade, namely lipofuscin. Therefore, a defective ABCA4 protein will result in the accumulation of lipofuscin in the photoreceptor and RPE level, which leads to RPE dysfunction at the early disease stage. So what I have here is an OCT scan from an eye with Stargardt disease. You can see outlined in yellow 2 lipofuscin deposits. And clinically, we know These deposits, they first arise at the level RPE, they move towards inner retina, past the ISOS, past the ELM, and impinging on the ONL. With disease progression, RPE will then lead to photoreceptor death, which then impairs vision. This is especially visually debilitating as this affects central vision. Typically, here's a fundus photograph from an eye with Stargardt disease, same eye across 9 years. You can see it's rather unremarkable if you just look at the fundus image. However, if we zoom in this central vision towards a later disease stage, and what I'm going to show here is an infrared reflectance photo from the same eye taken at the later stage. You can see the central patch of whiteness. This is area of atrophy. And if we were to zoom in towards with the OCT scan across this area of atrophy, and the arrowheads are demarcating where the edge of the atrophy is, you can see that there's no outer nuclear layer. Therefore, there's no vision in the central vision. Fundus autofluorescence is a commonly used technique in the clinic to assess the health of the RPE. And the function of the RPE is to provide support for the photoreceptors. And that's the first layer affected in Stargardt disease. So to record RPE, so to record FAF, we send specific wavelengths into the eye, and this will capture the fluorescent information from the RPE. This will then generate an unfast fluorescence map. There are two light sources we can use in the clinic to measure FAF. Firstly, IRAF, infrared autofluorescence, uses a reddish light source, and it's shown to measure the composition of melanin in the RPE. And secondly, you have shortwave autofluorescence, which is what we'll focus in this talk. It uses a shorter blue wavelength and measures the distribution of lipofuscin on the RPE. Before moving into Stargardt eye, let's just see what a short wavelength autofluorescence looks like in a healthy eye. So as you can see, we have even distribution of fluorescence across the macula, the shadows cast by the blood vessels, and lastly, you have this central patch of darkness, and this is arise by the absorption of short wavelength by macular pigments. And for reference, I'm going to put the same photo back up here, and this is an eye with Stargardt disease. And what becomes really apparent is you can see these patches of brightness scattered throughout the macula. These are called hyperautofluorescent flecks, and these are actually where the lipofuscin are deposited throughout the retina. This is an eye of a 56-year-old, and if we look across time, so over 7 years of disease progression, you can see firstly all of the flecks appearing over time. Secondly, you can see the flecks, they converge and become bigger across time before becoming patch of darkness as that RPE dies. And that's more apparent when you look at this particular set of images, this particular portion of the retina. You can see the brightness followed by patch of atrophy, and the atrophy grows as the disease progresses. So we can see visually there's an expansion away from the central retina as of these flecks as the disease progresses. So that brings us to the main research question. Is there a way we can measure, quantify these flecks over time? So one obvious way to do it, which is do it manually, but as you can see by the amount of flecks, that would take a long time. And secondly, are these flecks a suitable trial endpoint in Stargardt disease? And this is of importance to us because there are novel treatments being proposed right now for Stargardt disease. The approach we took in this study was to employ deep learning for image segmentation. More specifically, we utilize convolutional network called the UNet, which is specifically designed for image segmentation. This algorithm called the UNet is due to the shape of the architecture as shown here. Now, to my basic understanding, the left side of our algorithm involves spatial contraction of the input image, and then the feature extraction is increased as you go down the architecture. And the algorithm will then output a high resolution segmentation map via the processing steps on the right-hand side. Overall, the end goal of this algorithm is to identify each pixel within the image as a pixel of interest or not. In this case, whether that pixel is a fleck or not. So what does this mean in practical terms? In the first image, an algorithm has been designed to detect people in this image, as shown by the blue boxes. What we do here takes this to a step further. We'll segment all pixels of interest within the image. In this case, all pixels identify the algorithm as people are segmented, and you can see it here. And in this biological application, the algorithm has been trained to segment the cells within the image. Shown in yellow is the manual ground truth marked by a human, and the cyan map is marked by a trained algorithm. So what we did was we interrogated our clinical database and identified 24 Stargardt patients with biallelic mutation in the ABCA4 gene and with short wavelength autofluorescence imaging. In total, there are 24 participants, 12 female, 12 male, and the median age ranges from, the age ranges from 9 to 89 years old. And you can see the vision ranges from very good at 6.4.8 all the way to legally blind at 6.360. In the UNet architecture, the methodology involves giving the machine learning, giving the machine a set of marked data and allow it to learn about the information that's been processed. So therefore, we separated our images into 3 sets: training, validation, and testing. The training is used to train the model. Validation is to validate and adjust the model parameters during training. And this training and validation process undergoes reiterative tuning and evaluation. And then we have the algorithm, which we then use the testing set to test the performance of the model using data that's not involved in training and validation. This is so not to bias the system. Let's look at the characteristics of our Stargardt images first before we delve into the algorithm. We first examined the image collected. In doing so, we identified 2 types of fleck pattern. We have diffuse, as you can see, the little diffuse flecks here, or we have larger discrete patterns. So what we did was, altogether, there was 47 images, 16 diffuse, 31 discrete, and we have marked them manually using the blue outline here, as you can see. We then divided the 47 into 37 images for training and validation and 10 for testing. And by this stage, you might think 37 seems a bit low. So yes, that is true. So what we did was we utilized patch-based learning, in which each image was divided randomly into 50 patches. So we took 50 patches randomly at 112 by 112 pixel from the original image. This then gave us 1850 patches for training and validation, which we use 1750 for training and 100 patches for validation. And this is the UNet architecture employed in this study. So we have the raw 512 by 512 pixel input image, which undergoes a series of steps to output the segmentation map. The model training took 11 hours and total 138 epochs. Let's have a look at the performance of the architecture. So after we've developed the algorithm, we are now using the test images to assess the performance. So we have 10 test images, which underwent manual segmentation, as well as deep learning algorithm. And then we compare the results. Let's look at some examples. What I have here in panel A is the raw data for manual segmentation, before manual segmentation. In panel B, what we have in blue are the results from manual segmentation. And this generated a mask. In the row below, we have training results. We have the results from deep learning algorithm. Again, on the left, we have the raw image, then we have the segmentation image, then we have the mask. DICE score is used to evaluate the performance, 1 being perfect match and 0 being complete mismatch. And in this case, the DICE score is 0.8. This is an example of diffuse pattern. And you can see again, on the top row, we have raw manual, segmented manual, and the mask. And below we have the algorithm, segmented algorithm, and the mask. Again, in this instance, you can see on the upper right corner, there's a clear mismatch. And therefore, this one has a lower DICE score of 0.6. Altogether, for the 10 test images, the average DICE score was 0.64. Now we've developed the algorithm. The first thing we want to do is to use it to quantify the flecks. However, before we do that, we section our image into 3 concentric circles centered at the fovea. This is to provide uniform analysis across all images. You can see the ring diameters are 5, 10, and 15 degrees. And from each ring, we will then evaluate the fleck count, so the number of flecks, and the total area of flecks for that ring. What I have here is Bland-Altman analysis of fleck number. So this, on the y-axis, we have the difference between deep learning and manual. And on the x, we have the mean of deep learning and manual. The black solid line is the group average for the 10 images, and we have the 95% confidence interval. Firstly, at 10 degree in the innermost ring, in terms of fleck number, it seems fairly congruent. And a similar story is seen when we look at the fleck area. When we look at the middle ring, you can see that the average is still around 0 for both the fleck number and fleck area. However, the 95% confidence interval is wider in this case. And the story is similar when we move on to the outer ring. So the take-home message is that the average difference between the 2 methods is close to 0, which is good for both fleck number and fleck area. However, it does show a wide 95% confidence interval for both the middle and the outer ring, so there's room for improvement. So what we did next is we used the developed algorithm to apply it to analyzing longitudinal data. This eye has this example here has a pattern of diffuse speckles, diffuse pattern of flecks. And what I have here right now is the result of manual segmentation of this particular patient at 21 years old. The same analysis, so deep learning analysis was done, segmentation was done for the same patient, for the same image. And this is the same eye, 6 years' time. Again, on the left, we have manual segmentation, and on the right, we have deep learning. This is quantifying the results. So what we have here on the y-axis are fleck number in the upper row or fleck area across the time after first visit. In black, we have manual, and in unfilled, we have deep learning results. So for the central 10-degree ring, we can see that it's fairly stable over time. Now moving on to the middle ring, you can see both manual segmentation and deep learning for both fleck number and fleck area increases. There's a trend of increasing over time. And a similar story is seen when we look at the outer ring. However, I want to bring this to our attention. You can see that in this, just looking at the fleck number, manual segmentation tend to estimate more flecks compared to deep learning. However, paradoxically, the total area estimated is actually smaller using the manual, despite we're counting more. So that is something we'll investigate a bit further later on this talk. This is a pattern of discrete fleck appearance. Patient was first seen, a 56-year-old. This is the manual results at the first visit, deep learning result at the same visit, and then 6 years later, manual results, deep learning results. By looking at the quantification, we see a similar story compared to the previous slide. Again, it's a fairly stable, no sign of much progression for both fleck number and fleck area in the first ring. In the middle ring and the outer ring, what we can see is an increasing trend over time in both segmentation method. Again, there's a tendency for manual to count more flecks, but smaller overall size, the overall area. So altogether, we had 12 eyes with follow-up data. The average follow-up time was 4.2 years. These images were not used for deep learning training. This is not to bias the system. In total, there were 82 images analyzed. And what I have here is a bar plot. This is plotting, when you look at the y-axis, the difference between deep learning and manual segmentation in terms of fleck number for each of these three rings, and each bar represents each image. And you can see that there's a, as we showed in the previous two examples, there's a tendency for the manual segmentation to count more flecks compared to deep learning. You can see by these large majority of negative bars. However, if we look at fleck area, total fleck area within the three rings, deep learning tend to be estimating more fleck area compared to manual. So why is this happening? So we reviewed the image analysis procedure and we identify this CLA-HE, which is contrast limited adaptive histogram equalization, which is a contrast enhancing technique, which is commonly employed in image analysis prior to deep learning. However, you can see using this flowchart that when we segment the test image, these are actually raw images that did not undergo histogram equalization. So let's delve a little deeper. What I have here is side by side of the same image that underwent manual segmentation and deep learning. What you can see when you look in side by side, first of all, the contrast is enhanced on the right in the deep learning image. So let's look at fleck number. You can see in this particular example, crossing the blood vessel, what we did was in the manual segmentation, we segmented 2 flecks. However, with this contrast enhancement, this blood vessel is not as visible. Therefore, in deep learning, this was segmented as 1 fleck. Same applied to here. However, if you look at the fleck size, the act of enhancing that contrast actually made the fleck appear bigger. You can see by comparing these 2 images. And again, you can see on the right-hand side, the fleck area is bigger, and also here as well. So the limitation, this limitation of using CLA-HE can be rectified either by retraining the algorithm without the contrast enhancement step, or manual segmentation of the contrast enhanced images. So in conclusion, we have demonstrated that deep learning is a more efficient way to segment these flecks than manual segmentation. And also we have shown that these flecks, they tend to increase in size and number over time, and they precede central atrophy. So you can think of it as a more earlier stage of the disease progression. Therefore, it shows a potential to be a trial endpoint in Stargardt disease. So I'd like to thank my co-authors in this work. So we have the collaborators in LEI, Associate Professor Chen, Professor Mackey, and Dr. Maria Attia and Sukanya Aranchalam, and also the ophthalmic photographers, the computer science team at CSIRO with the architecture development, and also AIRDR for the genetic analysis. I'll be happy to take any questions.
Thank you, Jason. That was fantastic work. Very interesting. Yeah, just want to see whether there's any question and comments from the audience first. If not, then I'll take the initiative to ask the first question. One of my questions I always contemplate is, let's say if there are some clinicians in the audience and they want to bring this idea to collaborate with AI scientists, they want to develop AI algorithm to solve their own clinical questions. Normally, how many number of images do you think it's required? Because in the literature, there are a lot of algorithms that is developed with 100,000, that kind of order number of images for computer vision AI. But sometimes you can see only like dozens of images enough. So like in this example, yeah, in your study. So I just wonder if I'm a clinician and I need to solve one problem, for example, OCT segmentation or other clinical dilemma with AI, how many how many images with label that I need to prepare? Yeah.
That's a very good question, Chung, but I think, so from what understanding, so we are limited by the amount of images we have. So in this particular project, Stargardt disease, as with all retinal degeneration, it's a rare disease. And also to have both Stargardt disease diagnosis and the images. Therefore, in this study, we only have 40-odd images. So we talked with our collaborator, and there are ways to turn those 40 images into enough data set. So from some of the work I'm doing with some of the other AI scientists, from what I understand, so in addition to patch-based learning, which is what we did here by dividing the limited amount of images into multiple little patches, or they can actually rotate, change the contrast, or flip the actual image. So there are ways to, from what I understand, to manipulate the image to increase the data. But obviously, ideally, the more data, the actual real world, the more real world image data you have, the better. It just depends on the disease you have. Let's say if it's diabetic retinopathy, you have thousands of images, then there's no need for patch-based learning. That's my understanding.
Yeah, I fully appreciate the challenge of getting enough data, especially this data, that these patients that you follow for so many years, so tightly. It's definitely difficult to do when the number is in 100,000. It's almost impossible to have such a good follow-up over this many years. I think that the strength of this study is that, like, we also have very good follow-up to see the progression.
Yeah, we're very lucky. So the WARD study, which is the Western Australian Degeneration Study, run by Associate Professor Chan, we have, we have good enrollment, and we do try to get them to see us every 6 months so we can collect clinical data. And we're very lucky these participants are willing to donate their time.
Mm-hmm. Yeah.
So Jason, I have one question for you.
Yep.
Can you hear me? Okay.
Yes, go ahead.
More like from the AI scientist perspective. So some of the mask you show in the image is quite small. So normally in the machine learning, we call these small object detection. And so the baseline, the method used is the UNet. And so in order to improve the performance further, have you considered any modifications on the small object detection by modifying the UNet component?
Okay, yeah, so that's another very good question. So I will have to feed back to my computer science colleagues in CSIRO, and that's something that definitely worth doing to improve the performance of the architecture as you suggest.
Oh yeah, all right, thanks for that, Jason. Just one follow-up question for each image. So how much time does it take to do the labeling for every single segmentation mask?
So the discrete ones are much easier. The diffuse ones this took me sitting in front of a computer at least 2-3 months.
2-3 months.
I was getting cross-eyed towards the end.
Right, that's quite a lot, to be honest. So on average, how many minutes on average?
So I would say to do a complete sit down, about 30 minutes for a simple one, and for the discrete one, the simple discrete be 30 minutes or so, but the more complicated diffuse one would take close to an hour, if not more.
I see. Yeah, that definitely seems very complicated compared to other general, segmentation, right?
Yeah, it's a very onerous task, and I was glad we have developed this architecture, which will make my job a lot easier down the track.
I see. All right, thanks for that. That's my question.
Great questions. Just goes to show that what kind of challenges faced, not just the number of data and image, but also the label is a very critical part of this work. Jason, I just wonder, in terms of looking at the big picture, how this can benefit the treatment of Stargardt disease. Can you tell us a bit more how using this algorithm can benefit the treatment as a big picture? Do you see what kind of potential use in the whole treatment?
Yeah, that's a question we are trying to grapple with ourselves. But I think in response, so what we have shown is that these flecks, they will progress and proceed before atrophy starts. So if you have someone with Stargardt disease, then you can monitor their flecks, and then if you say put a treatment in there, and then the flecks, they don't progress over time. Therefore, in using the data from this study, therefore, it's one way of showing that disease has not progressed. Your treatment has worked, because naturally, both the area as well as the number of flecks will progress over time. So by stopping the progression of Stargardt, therefore you would think the fleck will not increase in size and number over time. And this is just for the early stage. So before you really have atrophy, once you have atrophy, unfortunately, you can't rescue what's already dead.
Right, thanks. Another question that I've been thinking is, it's interesting to see how manual segmentation will give you more numbers and less area compared to AI algorithm. And that makes me wonder whether the AI algorithm is still less sophisticated in doing this task. For example, a human grader will make more finer counting. Is like if there are two dots that are quite close adjacent to each other, human grader can see that as two little flecks, but the AI may see that as one coalesced flecks. Is that, do you think that is possible?
That is possible, but I also think that maybe using the contrast enhancement step during the AI training process artificially enhanced the appearance of these flecks. Therefore, in our data, there was a mismatch between AI and manual segmentation. So one way to test that theory is to either retrain the algorithm within raw images without doing the contrast enhancement. That is my preferred way, because the other way will be me segmenting the contrast images.
I can understand why you want to go one way, not the other. Fully understand. Yeah. Interesting. Just wondering whether there's any more comments. I can see this is, what's the next step? Is there going to be a real trial in real patients?
So there are some trials being proposed, and for us, we're also working on other retinal degeneration diseases. So I'm lucky enough to have a ophthalmic research institute Australia fund to look at RP images, so images in patients with retinitis pigmentosa, and we're also working with a AI team in QUT trying to come up with a way to analyze these images more efficiently as well. So for us, we are open to analyze any diseases with inherited retinal degeneration, and for us, we want to be able to come up with ways to more efficiently analyze these images so we can analyze our functional and structural data better.
That sounds very promising, and yeah, looking forward to the outcome of your clinical trial, and we can maybe in the future hear more about it.
I'll be glad to.
Yeah, I just want to see whether if there's any more burning questions from the audience. Otherwise, I think we can close out today. I just want to thank you again, Jason. It's fantastic work. It's great to hear about your talk. And I can see there's a lot of potential, and hopefully you can find some excellent findings in your clinical trial. We will keep an eye and look forward to any update in future.
Thank you, Zen, and thank you, Zhongrong, and thanks for the opportunity.
Thank you, Jason. Thank you very much for the talk. Wonderful.
Yeah, and thanks very much, everyone in the audience for your participation. And hopefully you can, we can keep an eye on our future episodes. We will continue to have excellent speakers about on this AI topic on healthcare. So until next time, we'll see you.
Thank you.
Thank you.
Bye.